Welcome back to my audio physics classes. Now today we'll discuss about the mirror formula or formula related to mirror. The focal length of a spherical mirror of a radius R capital R is given by F equals to R by 2. Where cap R is the radius of curvature of the mirror and F is the focal length. Focal length is represented by a small f. F and R is negative for concave or converging mirror and it is positive for convex or diverging mirror. The power of a mirror is defined as 1 by focal length in meter minus 1 by focal length in meter, and it is represented by P. So power of mirror is P equals to minus 1 by F in meter, and it is also equal to the minus 100 by F when F focal length in cm. If focal length is in meter, then power will be equal to minus 1 by F, and if it is in centimeter, then it will be equal to the minus 100 by F. And the unit of power is diopter. Example, if the focal length of a converging mirror is 50 centimeter, its power will be minus 100 by minus 50 equals to plus 2d. Diopter is represented by capital D. Next point. If a thin object of linear size HO is situated vertically or O is situated vertically on the axis of a mirror at a distance u from the pole, and its image of size I is formed at a distance v from the pole, then magnification, it is also called transverse magnification, is given by m. Magnification is represented as small m. M equals to I by O, where I is the image size and O is the object size, and m is also equal to minus v by u, where v is the image distance and u is the object distance. Here negative magnification states that image is inverted with respect to object, while positive magnification clears that image is act with respect to object. Now mirror formula is given by 1 by v plus 1 by u equals to 1 by f. Here we know that v represents image distance, and u represent object distance, and f represents focal length of the mirror. For using this formula, we should place all value with proper sign. So mirror formula is 1 by v plus 1 by u equals to 1 by f. Again, now we see the formula for longitudinal magnification, and this is the case when object is placed along the length of principal axis or parallel to the principal axis. Then we use longitudinal magnification given by ml equals to I by O equals to minus V2 minus V1 by U2 minus U1 or equals to minus dV by du, or here I represent linear or longitudinal size of image, and O represent longitudinal size of object. Some important point also we see here. We know that the mirror formula is 1 by V plus 1 by U equals to 1 by F. Now if we differentiate it, we will get minus dV by V square minus du by U square equals to 0, or dV by du equals to minus of a square of V by U. Hence, longitudinal magnification ml equals to minus dV by du equals to a square of V by U equals to m square. That is, longitudinal magnification is equal to the square of transverse magnification. If a 2D object, two-dimensional object is placed with its plane perpendicular to the principal axis, its magnifications is called superficial magnification and will be given as superficial magnification is represented by ms, m suffix s, or equals to area of image divided by area of object, which is equal to the m square again. In case of more than one optical component, the image formed by first component will act as object for the second, and so overall magnification m equals to I by O equals to I1 by O into I2 by I1 into I3 by I2 into I4 by I3 dash 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 equals to M1 into M2 into M3. Next point. Let's see some discussion about image formation. For a real extended object, if the image formed by a single mirror is erect, it is always virtual. That is, M is positive. If magnification in this image is virtual, means magnification is positive, and in this case the size of image is smaller than object if the mirror is convex. First, second, if the size of image is equal to object, the mirror will be plane, and if the size of image is larger than the object, the mirror will be concave. So, by observing the size of image, erect image in a mirror, we can decide the nature of the mirror, whether it is convex, plane, or concave. Again, for real extended object, if image formed by mirror, single mirror, is inverted, it is always real, and in this case magnification is negative, m is negative, and the mirror is concave. And in this case, if the size of image is smaller than object, then object is between infinity and center of curvature, and image is between focus and center of curvature. Second, if the image size is equal to object, then it is at center of curvature and image center of curvature. If size of image is larger than object is between center of curvature and F, and image is between center of curvature and infinity. Note next point. At every we know that every part of a mirror forms complete image. If a part of mirror is obstructed or blocked with a black paper or any other paper, full image will be formed but intensity will be reduced. If an object is moved at constant speed towards a concave mirror from infinity to focus, the image will move slower in the beginning and faster later on away from the mirror. It is because in the time object moves from infinity to center of curvature, the image will move from focus to center of curvature. And when object moves from center of curvature to focus, the image will move from center to infinity. At center of curvature, the speed of objects and image is equal. We have a formula for focal length of a spherical mirror given as f equals to r by 2. It only depends on the radius of mirror and it is independent of wavelength of light and refractive index of medium. So the focal length of a spherical mirror in air or water and for red or blue or any other single color light is same. This is also why the image formed by mirrors do not show chromatic aberration. Again, in case of a spherical mirror, when radius of curvature tends to infinity, it becomes plane. And we know that focus is given as f equals to r by 2 and focal length will be infinity. The mirror formula, from mirror formula 1 by v plus 1 by u equal to 1 by f reduces to 1 by v plus 1 by u equal to 0, and in this case v equals to minus u. That is, image at same distance behind the mirror as the object is in front of it. This in turn verifies the correctness of mirror formula. Now let's see Newton's formula for the mirror. Consider in a spherical mirror, if object distance is x1 and image distance is x2 and are measured from focus instead of pole, then u will be equal to f plus x1 and v will be equal to f plus x2. So the mirror formula 1 by v plus 1 by u equals to 1 by f reduces to 1 by f plus x2 plus 1 by f plus x1 equals to 1 by f. After solving this, we get x1 into x2 equals to f square, and this is called Newton's formula for mirror. Again, if in the case of a spherical mirror, if we draw a graph between first 1 by u and 1 by v, the graph will be a straight line with intercept 1 by f with each axis. Because 1 by v plus 1 by u equals to 1 by f takes the straight line equation y plus x is equal to c with c equals to 1 by f. Again, if we draw the graph between u and v, the graph will be hyperbola. As for u equal to f, v equals to infinity, and for u equals to infinity, v equals to f. And again, a line u equals to v will cut this hyperbola at 2f comma 2f. Concave mirror behaves as convex lens, both convergent, while convex mirror behaves as concave lens, both divergent.